ozone non-attainment areas other than Southern California don't need air cleaners to meet Standard 62, but designers might want to consider using them anyway. After all, breathing ozone is harmful, and besides that, if you're designing a high-performance building, Standard 189.1 requires 40% efficient ozone air cleaners in all ozone non-attainment areas, which includes most of California and many major metropolitan areas throughout the U.S.
As Dennis mentioned, we're only going to focus on the ventilation rate procedure for today's program. This procedure includes both zone calculations and system calculations. First, the outdoor airflow needed in each ventilation zone must be determined based on prescribed rates listed in a table. Then, based on these zone calculations, the outdoor airflow needed at the intake for the entire system must be calculated, using procedures and equations defined in the standard. Paul is going to start out by explaining the zone calculations. Paul?
Standard 62 requires a three-step procedure to determine the outdoor airflow required for any occupiable space, which the standard calls ventilation zone. I'll tell you about those 3 steps and then dive deeper into each one. First, we calculate the volume flow of outdoor air, V sub Bz, that must be delivered to the breathing zone within an occupied space, using the prescribed rate in Table 6-1 of the standard. Next, we determine the zone air distribution effectiveness, or how well the ventilation air mixes in the space, which depends on the location of the supply diffusers and return grills. The standard provides default values in Table 6-2 for different air delivery configurations. Finally, we calculate the volume flow of outdoor air required for the zone by dividing the breathing zone outdoor airflow by the air distribution effectiveness. Before I show an example of breathing zone calculations, I would like to talk about Table 6-1, the minimum ventilation rates in the breathing zone. Standard 62 specifies minimum ventilation rates to both dilute space traditional contaminants to safe concentrations and to satisfy the olfactory senses of the occupants. Occupant satisfaction relates to the perceived intensity of odors and irritants from 2 major sources, the occupants themselves and the building and its furnishings. While the actual relationships are complex, most experts agree that the best simple model for effective dilution of odors and irritants involves summing the outdoor airflow needed for each of these sources. As a result, since 2004, Standard 62 has prescribed 2 ventilation rates for each occupancy category. R sub P, the rate for people sources, and another, R sub A, the rate for building-related sources. This table shows prescribed minimum rates for several occupancy categories. Earlier versions of this standard prescribed only 1 ventilation rate for each category. This single rate accounted for the additive nature of odors and irritants, but did so behind the scenes. For example, the 1989 version of the standard required 20 CFM per person for offices. Behind the scenes, that was 15 CFM to dilute people-related odors and an additional 5 CFM to dilute building-related odors. But these old CFM per person rates penalized high occupant density zones, like conference rooms or theaters and churches. By accounting for people-related and building-related sources separately, the new approach, which some call additivity, results in lower ventilation rates for high-density spaces. Now back to our 3 steps necessary to determine the volume flow of outdoor air for a zone. Let's exercise the first of these 3 steps for zone calculations by using a simple example. In step 1, we determine the occupancy category for the zone using Table 6-1 and identify the corresponding ventilation rates. This includes 2 components. First, the people source outdoor airflow rate, which is called R sub P and is quantified in terms of CFM per person. And second, the building source outdoor airflow rate, which is called R sub A and is quantified in terms of CFM per square foot. Then we determine the peak population for the zone P sub z, and floor area, A sub z, and solve this equation to find the required outdoor airflow for the breathing zone. Side note here, you can use average population for P sub z, but that requires knowledge of an occupancy profile. The calculation for this is too long to fit here, but will be included in the supplement at the end of this broadcast. As an example, let's consider a 1,000 square foot office that has a peak population of 5 people. For an office occupancy classification, Table 6-1 requires 5 CFM of outdoor air per person plus 0.06 CFM per square foot of floor area. Plugging these 4 numbers into the equation, we find that the standard requires 25 CFM of outdoor air to dilute the people-related sources plus 60 CFM to dilute the building-related sources. So in total, the zone requires 85 CFM of outdoor air delivered to the breathing zone. Let's look at one example. Again, 1,000 square foot zone, but this time it's a conference room designed for 17 people. The Table 6-1 requirements are the same for a conference room as they are for an office in our previous example. 5 CFM per person plus 0.06 CFM per square foot. When we solve the equation, predictably, the conference room needs the same 60 CFM outdoor air as the office space to dilute the building-related sources. But it needs 85 CFM to dilute the people-related sources due to the higher occupancy. In total, the conference room requires 145 CFM of outdoor air compared to 85 CFM for the office. Okay, back to the 3-step zone calculation process. Using the prescribed rates in Table 6-1, we just used equation number 1 to determine the volume flow of outdoor air that must be delivered to the breathing zone. We now move to step 2, the determination of the effectiveness of the zone air distribution, E sub z, which is based on how the air is delivered to the space. E sub z helps the designer to account for ventilation air that is delivered to the space by the diffusers, but bypasses the actual breathing zone. E sub z is simply a lookup. In Table 6-2, the standard provides default values for 10 different air distribution configurations. Here's an excerpt from that table. You can see that it's based on placement of supply diffusers and return grills, and the temperature of the air being supplied. For most zones, air distribution effectiveness will be 1 during cooling operation. During heating operation, it may be less than 1, since warm air tends to float above the breathing zone air or rise quickly through it. In either heating design, the air doesn't perfectly mix in the breathing zone, and therefore doesn't do a good job of diluting contaminants. Now that we know both the volume flow of outdoor air to the breathing zone and the effectiveness of the air delivery system, we can calculate the volume flow of air that must be delivered to the space. V sub OZ is simply the required flow to the breathing zone divided by the effectiveness of its delivery. Going back to our office example, the outdoor airflow that must be delivered to the breathing zone is 85 CFM. During the cooling mode, cool air enters the space through the overhead diffusers and returns through grills in the ceiling. From Table 6-2, we find the zone air distribution effectiveness to be 1. This means that delivering cool air from overhead diffusers is 100% effective at getting the outdoor air into the actual breathing zone. So solving the equation, we find that 85 CFM of outdoor air must be delivered to the diffusers so that 85 CFM makes it into the breathing zone. No air bypasses in this mode. But what about during heating mode? If hot air enters the space through the same overhead diffusers and exits from overhead grills, Table 6-2 indicates that the zone air distribution effectiveness is only 0.8. When supplied and returned overhead, the buoyancy of this hot air will tend to cause some of the air to bypass from the diffusers to the ceiling-mounted return grills. So this system configuration is less than 100% effective at delivering outdoor air from the diffusers to the breathing zones. In the heating mode, we find that 106 CFM of outdoor air must be delivered to the overhead diffusers so that 85 CFM makes it into the breathing zone in this office. In this mode, 21 CFM of outdoor air bypasses the breathing zone altogether. This next slide compares the various methods of distributing air to the zone and how the default values for air distribution effectiveness impact zone outdoor airflows for our office example. First, notice that E sub z for most common configurations is 1. Two configurations that have an effectiveness less than 1 are when hot air is delivered through ceiling-mounted diffusers and it also returns from the ceiling, or when warm air is delivered through diffusers in or near the floor and it returns from the ceiling. However, notice that if you design the system so that the supply air temperature during heating is less than 15 degrees above the space temperature, and if the diffusers are selected to achieve suitable velocities, you can achieve an air distribution effectiveness of 1, even with overhead heating. This should be the design goal. The only configuration that has an effectiveness greater than 1 is when you deliver cool air using true displacement ventilation. Finally, these last two configurations were added to address systems where the outdoor air is drawn into the room. A common example is a hotel in which the outdoor air is delivered to the corridor and then drawn into the individual guest rooms underneath the door.
So that covers the zone calculations of the ventilation rate procedure. Next, John will explain the system calculations. This involves calculating the outdoor airflow needed at the intake for the entire system and builds on the zone calculations we just reviewed. John?
The ventilation rate procedure of Standard 62 defines 3 ventilation system configurations: single zone, 100% outdoor air, and multiple zone recirculating systems. The procedure for calculating the system-level outdoor air intake flow differs for each of the configurations. But in each case, the system calculations build on the same zone calculations that Paul just explained. In a single zone system, one air handler serves the ventilation needs of one zone. All the outdoor air that enters through the intake is delivered to that single zone. Any recirculated air is merely return air from that same zone. Some examples of single zone systems include packaged terminal air conditioners, classroom unit ventilators, or small packaged rooftops. In a 100% or dedicated outdoor air system, one air handler serves the ventilation needs of more than one zone. Outdoor air enters through the intake and is then delivered to the zones without mixing it with any recirculated air. That is, the dedicated outdoor air unit delivers only outdoor air, not a mixture of outdoor air and recirculated air. Local units then handle the cooling or heating loads within each zone. These local units are typically fan coils, water source heat pumps, small DX split systems, or VRF terminals. Or they might be small rooftop units, chill beams, or even radiant ceiling panels. In a multiple zone recirculating system, one air handler serves the ventilation needs of more than one zone. But in this case, after the outdoor air enters through the intake, it mixes with recirculated air before being delivered to the zones. The most common example is a conventional multiple zone VAV system. Also, for some applications, active chilled beams may require primary airflow that is greater than the minimum ventilation requirement. In that case, if they recirculated air, they are also multiple zone recirculating systems. To demonstrate the procedures for calculating system level intake flow, we'll use this very simple 3-zone example. As I mentioned, for each of the 3 configurations, the system calculations build off of the exact same zone calculations. So for our example, the zone outdoor airflows have already been calculated to be 300 CFM for zone 1, 400 CFM for zone 2, and 500 CFM for zone 3. We'll demonstrate the system calculations assuming operation in cooling mode. So zone air distribution effectiveness is equal to 1 in each zone. but I will mention how the results might change in the heating mode later on. Now, starting with a single zone system. Since all the outdoor air enters through a single intake and is then delivered to one zone, this calculation is pretty easy. For our example, we're assuming that a separate rooftop unit serves each of the three zones. According to Standard 62, the required system intake flow, V sub OT, is equal to the corresponding zone outdoor airflow, V sub OZ. So V sub OT equals 300 CFM in the cooling mode for the system serving Zone 1, 400 CFM for the rooftop serving Zone 2, and 500 CFM for Zone 3. Note that if E sub Z is less than 1 during heating mode, the system intake in a single zone system may need to be higher. Now let's move on to the 100% outdoor air system. For our example, we're assuming that a dedicated outdoor air unit delivers conditioned outdoor air directly to all three zones, and a fan coil in each zone provides heating or cooling. In this case, since the ventilation system delivers only outdoor air and no recirculated air, the required system intake flow, V sub OT, is simply the sum of the zone outdoor air flows. So for our example, the intake for this dedicated outdoor air unit needs to be 1200 CFM, or 300 plus 400 plus 500. Now for the multiple zone recirculating system, which is more challenging.